really need to change my keyboard shortcuts for that. Okay. Some more super fancy slides for you. That's my specialty. All right, sets. So a set is just a list where all the items are unique, and the elements from a set come from some domain or universal set of items. So a set is always in the context of some domain, okay? And I'll talk more about that in a minute. So some examples are, if we say the domain is all pets, then one set in that domain could be dog, cat, bird. So if the domain is all different kinds of pets, then that's one example of a set. If the domain is all modes of transportation, one set in that domain could be car, plane, bike. So a set is always in the context of a domain, and the items in a set are unique. You don't have duplicates. So that's two concepts to understand. Sets in maths, we use some notation, and we're generally talking about numbers and not pets or modes of transportation. But there are applications of set theory outside of maths, but we're going to kind of focus on the maths applications of set theory and use that to talk about the notation and the operations. So the domain is the larger collection from which a set is a part. An element is an item in the set. A subset is one set that's contained within another set. And a subset could be an exact copy of the superset. When it's not, when the subset has less elements than its superset, then we call that a proper subset. So a proper subset has less items than the set that it's a subset of. And then the superset is just a set that contains another set. And same thing there. A superset could be the same as the set that it's a superset of, but it's a proper superset when it's bigger. Okay, we'll look at some notation for these in a minute. But you've used these terms most of your life probably, subset at least. Maybe you haven't used superset very much, but we're familiar with the term subset and what a subset is. So we can combine sets, and this is going to be really reminiscent of Boolean logic and combinations, because it's the same thing really. So a union, what kind of Boolean operation is that like? Yeah, exactly. It's an OR. So a union contains all the elements that appear in either set, right? And an intersection is like an and it's I'm missing a parenthesis there. I know it says it on the slide, but you know, you may not be paying that much attention. So an intersection are the items that are in both sets, but not just in one or the other. And the way that I remember which one intersection is, and that it's and, is because the symbol for intersection is like a curvy and symbol. You know how the and symbol is the caret symbol? And so they look similar, and that's how I keep them straight, what intersection is and what union is. Also union, you think, you know, in my mind, union correlates to me with more, and intersection is, you know, last when you look at the Venn diagram, that clearly, like if you had to pick which one of these is union and which one is intersection, just looking at the Venn diagrams, you'd be able to pick it out, wouldn't you? So there's a little bit of benefit there in those words and what they mean to us already. They don't. Oh, you mean like and intersection and well, they're not exactly the same thing. They're similar things. But a Boolean operation considers two distinct Boolean values, and there'll be a result of that. Here we're talking about sets, so we're talking about groups of items. And so we have, you know, one group of item and another group of items. And the items that those two groups have in common is the intersection. And all the items in both groups forms the union of those two sets. So it's a little bit different, but there's definitely some similarities in the two concepts. So complement is like not. Okay, so complement is elements in the domain that are not in the set or in either set. So we can have the complement of a single set, and that would just be everything in the domain that's not in the set. And complement is where you really start to see why a set is always in the context of a domain. Because if it's not in the context of a domain, a complement doesn't make any sense, does it? You know? So we're always talking about a set of things in a larger domain, so that we can talk about the complement of that set. The difference between two sets is order dependent. So if I say A, the difference between A and B, and I put the A first, then what I'm saying is all the things that are in A that are not also in B. And if I wrote this the other way, the difference between B and A with B written first, how would this diagram look different?
B would be shaded into A.
That's right. So this piece right here would be shaded in. It would be all the elements in B that are not also in A. So this one, you have to remember that the order of these two is important. You have to consider that with the when you consider the result. And then there's one in set theory that's referred to as the symmetric difference, and what this is exclusive OR. Okay? So the symmetric difference, and again, when you look at a Venn diagram, that name kind of makes some sense, but the symmetric difference is all elements that are in either set but not in both sets. Okay? So it's like the difference of it's like I don't want to use the word minus because it's not really minus, but it's, you know, the difference between A and B combined with the difference between B and A. Right? It's like we take the union of those two differences, and that's our symmetric difference. Okay? All right, so let's look at some notation. So what we have at the top of the slide here is two sets, A and B. And we'll say that these sets, we don't have any complement here, so I didn't put anything about the domain, but we could say that these sets are belong to the domain of natural numbers, for example. So does everybody know what the domain of natural numbers is? I have another slide that talks about that in a minute. But the natural numbers are like the counting numbers. So it's positive integers starting from 1 are the natural numbers, or positive integers excluding 0 is another way to say it. So if we have A is 1, 2, 3 and B is 3, 4, 5, then the union, and you can see the notation for union there, the union of those two sets is 1, 2, 3, 4, 5. Now, you might notice that both A and B have a 3 in them. But when we write the union, we are also referring to a set. So there are no duplicates. Okay? So the set that is formed by the union of the sets A and B would contain 1, 2, 3, 4, 5. Not 1, 2, 3, 3, 4, 5. Okay? The intersection of A and B are any elements that are in both. And in this case, the only element in both is 3. Right? So the intersection of A and B, that set would just be 3. The differences. So if we look at the difference with A listed first, then we have 1 and 2 because 3 belongs to B. So we don't include that in the difference. And the difference with B listed first, so the difference from between B and A is 4 and 5 because 3 is included in A. So we don't include that in that difference. It's only the elements in B that are not in A. And then the symmetric difference is, you can think of it as the union of these two differences, like I mentioned. Or you could also think of it as the elements that are in A or B and are not in both. Okay? So the exclusive OR. of those two sets is another way to think of it. Any questions about that notation or those relationships?
Is there a notation for complement?
There is, and I should have put it on the slide. So let's do that one. Let's do that one now. So, and if we're going to talk about complement, probably I left it off of here so I could talk about some other set notation in a minute. But the
Yeah, it's also not on the slide with the Venn diagram either.
right, the notation you mean?
Yeah.
Yes. So typically the way you see the complement is with like a tick mark after the letter for the set. So if we said that A and B are elements of, and I have to go grab that character. This little character. Are elements of the natural numbers. Okay? If we said, well, what we could show here is the complement of the symmetric difference. No, we won't do that. We'll do the
Complement of the union.
complement, either any of these I'm going to have to give you some other set notation.
You could make it rather than the sort of all natural numbers, you could do just 1 to 10, something like that. Would make
Yeah.
it easier.
Yeah.
Can you just complement A, or do they need to be two sets?
No, they don't have to be two sets. So I can say the complement of A. So if I say that A is they're both, and I say further that A is
I now see why you didn't.
yeah, all numbers. Because to be really rigorous about it, you need to
It is in the actual unit though.
yeah, okay, all right. I'll add something to this after. I'll think more about how I want to put it in there so I don't confuse anybody. But there is notation for complement, and it's generally the little like tick sign after the letter that represents the set. That's all right. We'll look at some examples so I can try to make it more clear. So here's some more notation for subset. So if we have the set A is 1, 2, 3, and the set B is 1, 2, 3, 4, 5, then we could say that A is a subset of B. Does that make sense to everybody? Because the elements in A are also in B. And we can also say that A is a proper subset of B because there are elements in B that are not in A. Okay? And we could likewise say that B is a superset of A and that B is a proper superset of A for the same reasons. It's just the opposite way of saying it. So those are the notations for subset, proper subset, superset, and proper superset. Okay? So some common domains in maths are the natural numbers, which are the integers above 0, integers, which are all positive and negative whole numbers. There are other ones, but I didn't put them on here because I didn't want to talk about rational versus irrational and real versus complex numbers, because you don't really have to understand that for what you need to do in this course. Okay, so but there is a hierarchy here. So one is natural numbers are a proper subset of integers, and integers are a proper subset of rational numbers, and rational numbers are a proper subset of irrational numbers, and irrational numbers are a proper subset of real numbers. And there's this hierarchy in math. So let's just focus on natural numbers and integers, because I think we're all pretty comfortable with natural numbers and integers. So we can say, like I mentioned, that natural numbers are a proper subset of integers, and integers are a proper superset of natural numbers. Does that make sense to everybody if I say those words? So natural numbers are just integers without 0 in the negative numbers. It's just all the positive integers. So then when we see notation like this, the way that we understand it is that we're defining a set called A in this first one, and we're saying that the elements of A that's represented by X here, we're saying that the elements are in the domain of natural numbers. Okay, so they belong to natural numbers with an additional condition that they're less than 5. Okay, so the set of A, another way to say that is the set of A is all natural numbers less than 5. All right?
The x straight line just that's just your element. Like
Yeah.
Your element is
X.
this.
Yeah, so we're just naming this element so we can refer to it in sort of the clause that defines the properties of an element of this set. Okay, that it's an element of natural numbers, or it belongs to the domain of natural numbers, and that it's less than 5. So this set is comprised of all natural numbers less than 5. So what would that set look like?
1, 2, 3, 4.
That's right. We'll do the complement of this in a minute after we go through the rest of these. We'll do the complement. So what about this one? What are we saying here? This is an I, by the way. That's terrible font choice there. That's an I. So what does this one say?
So x is an integer
Yeah.
greater than -3 and less than 3.
Yeah. So what's another way to say that that might be a little bit?
A is the set of all integers between -3 and 3.
Yeah. Yes. Exclusive, right? So not including -3 and 3, but all the
Yeah.
integers between those numbers. So what would that look like?
-2, -1, 0,
Mm-hmm.
1, 2.
Yes, exactly. Does that make sense to everybody else? Okay. So, what about this one? So we have a set A, 1, 2, 3, and then we have a set B. And how is that set B defined?
All natural numbers less than 10 that aren't in A.
Yes, exactly. Exactly. Can everybody else see that? So
Very
that
thin line.
it is a thin line. It is. I'll fix that too. But what would this look like?
4, 5, 6, 7, 8, 9.
Yeah, that's right. So less than 10 and not 1, 2, 3 natural numbers, right? So that's exactly right. Let's see. If I bold it, that's a little bit better. Yeah? That's better. Okay, so any questions about that notation? So it looks really strange when you see it at first, but if you understand, if you look at some examples, I think it's not too hard to understand it. The trick with being able to translate this notation is just to take it a little bit at a time, make sure you understand each piece of it, and then you can write it out in English if you want to, so that it makes more sense. And you can have as many conditions lined up in there as you want, So there's not like a limit how many conditions you might see listed in that notation. So there we've got 3 in the last one. X is natural numbers, less than 10, not in A. So 3 different conditions that we have to consider when we calculate what that set B is comprised of.
A set can be empty, right?
A set can be empty, yes. Absolutely.
You're doing like greater than and less than. Can you do things like, divisible by?
Yeah, absolutely.
Just not plus or minus.
No, so you don't, you think of these as like conditions, So when you are comparing X to some value, you'll be considering these conditions. So, x is not an element of A. So for any value x, that will be true or false on it. X is less than 10. For any value of x, that'll be true or false. So these are always conditionals that return a true or false given some value of x. So they're not any other kind of operation. They always return a Boolean, those conditionals that are listed there. So you'd have something like, if you wanted to see if it was divisible by 3, you might notate it as like x modulus 3 equals 0 or something, you know? So it should always be returning a Boolean.
Could you use like the plus or minus if you had like x is the numbers in A plus 3? Like,
That would be like a set. You might, yeah. I think that there are cases where you might see some notation like that. Yeah. But don't worry about it. Okay, really, all you have to be able to do for this, for the understanding for this test and for this unit is just to recognize the notation, understand the different operations, and the terminology like subset, superset, domain, those terminologies. Okay, so don't get too bogged down in other things. And that's it. So if we have a look at what's in the Canvas unit, there's some other examples here that are non-math related. And then there are some math examples. So there's mention of natural numbers, and there's some set notation similar to what we just saw. There's a bit here about set operations and some Venn diagrams with examples, and then a description of the operations that we went through with some examples. A bit about subset. Here's something with complement. So he wrote it with a C. That's another way you might see it. I've always seen it with the tick sign after the letter. One thing about notations, particularly regarding sets, is because sets are used in so many different areas. You know, set theory is used in mathematics, and it's used in logic, and it's used in these different areas. And what you'll see is there's different notation in different practices. And that can be super confusing. So you just have to know for the given thing that you're studying what the notation is for that thing. So you might see it with a capital C. I've actually never seen that before, but I'm sure that that's in some sort of set theory that's how it would be denoted. I've always seen it with a tick sign after the letter. Another way you might see it is some indication of not. You know, so the little like line with the line down, or a line over the top of it to indicate not is another way, because the complement is basically not that thing. So there are some challenges here in the Canvas unit that are pretty straightforward, I think. Yeah, so I think that those are pretty straightforward. And then there's an opportunity to write some code here in the challenge to write functions that return the union, intersection, difference, and symmetric difference given two sets. That's what that challenge is about. And then there's a video that you can watch if you want to. He'll explain it a different way than I did. Any questions about that? There's not much to it that you need to understand for the purposes of the test. These are things that you're using to some extent when you write code anyway already. You know, to solve certain problems, you're going to be using these concepts. It's just sort of...
For the notation for those examples where it's like the x is all real numbers less than 10. It's basically like doing a 4x in an array of numbers.
Yes.
Where this parameter is true.
Within a certain range, or within a certain range or something like that. It is, yes, yeah. Yeah, that's true too.
Sounds good to me.
That's true too. Okay, so give the challenge a try, and if you get stuck on any of it, raise your hand so I can come over and we'll talk about it together. All right, but I think you'll be able to do it pretty easily. This one is a beast mode challenge, writing code to implement those things. Don't feel like you need to be able to do that, but you're welcome to give that a go.
Can we use that on the exam?
I'll look at the exam to see if there's any code related to sets. There are some code questions on the exam. You'll see that reflected in the review. There
Is it
weren't.
Paper exam?
It's a Canvas exam.
Okay.
It's similar to Ruby test. So there's there'll be questions. You have like a space to fill stuff in. Certainly though, when we do that test, we'll make sure that you've got some paper and a pencil, because I can't do math without paper and a pencil. So that you can write stuff down and then translate the answer to Canvas. Yeah.
So theoretically, we could write code for all of these union intersection difference, symmetric difference, and then use that.
Use that on the test. Sure. Absolutely.
That would be cool.
Yeah. All
I
right.
mean, if